In this ninth day, following the previous formulae which we built in the last class, we will go through some problems. Now, first one, uh, we are given a homogeneous partial differential equation of order 3 as we know, d means del x and d dashed denotes del y. So this is the problem. Now to start with, what we see that this is actually you can take a d common, then this will be d square minus 4 d dashed plus 4 d dashed square, that is d minus 2d dashed square working on z. So the complementary function, you can write it as we have seen beforehand, that this will be a function of y plus a function of y plus 2x and x multiplied with another function of y plus 2x, because there is a multiplicity of occurring of d minus 2d d dashed. Now for the particular integral, so we need to do it's like we write d minus 2d dashed square is being applied on 4 sine 2x plus y. So 4 goes behind d minus 2d dashed, keep that, and there will be a 1 over d sine 2x plus y. Now 1 over d is actually integration with respect to x, right? Now where you treat y to be a constant, so this part turns to be minus half cos 2x plus y. Now this operator will be working on this part, so what we have, minus 2 x square 1 square 2 factorial cos 2x plus y. Okay, so finally this cuts up and we have minus x square cos 2x plus y. So CF plus PY, that will be the solution. So next problem, d square minus 3d dashed plus 2d dashed square applied on z is equal to e to the power 2x minus y plus e to the power x plus y cos of x plus 2y. So we will break it like d minus 2d dashed d minus d dashed. Okay, so CF is phi 1, an arbitrary function of y plus 2x plus phi 2 y plus x, and the PI 1 by 1 if we calculate, say first for this term e to the power 2x plus 2x minus y. So we are writing this is PI 1 and this is for this first part, and then that will be d, we are writing the whole 3d dashed plus 2d dashed square is applied on e to the power 2x minus 1, and we will input in the place of 2 in place of d we will write 2, and in place of d dashed we will write minus 1, and you can see this will be 1 over 12, and this part is integration. We are assuming that 2x minus y is equal to v. So e to the power v dv. So finally it gives us e to the power v only, and so 1 over 12 e to the power 2x minus y will be the first particular integral part. Okay. And for the next part, pi2. So this is for e to the power x plus y only. Then we will break it because there will be a 1 over 0 else. D minus 2d dashed e to the power x plus y. So for this first part, it will be 1 over 1 minus 2 multiplied by 1 e to the power v dv. So this is minus 1 e to the power v simply. So we have d minus d dashed minus 1 e to the power v, but or rather x plus y, whatever you write. But for this part, the second formula, that is 1 over 0 formula, will be applied. So this is this, so minus x e to the power x plus y. This is the pi for the second part. And not changing the page, let's try to do the pi3 here only for the cos of x plus 2y part. So there this is, you just replace d by 1 and d dashed by 2, and then we have 1 minus 6 plus 8. So this part 1 minus 6 plus 8 is 3, and integration cos v dv, where v is x plus 2y. So this is 1 over 3. First integration is giving sine of v dv, and second time integration is giving 1 over 3 cos v, and 1 over 3 cos of x plus 2y. So now we have to add CF plus pi1 plus pi2 plus pi3, and that will be our solution. Well, so next problem. Let's do this one. So this can be written in d minus 3d dashed whole square, right, written as. So CF will be simply phi1, an arbitrary function of y plus 3x plus x phi 2 y plus 3x, and pi for this part d minus 3d dashed square tan y plus 3x. Now if we put these values directly, then there will be a 0, so we are writing as this will be x square 1 factorial, sorry 2 factorial 1 square multiplied with tan y plus 3x. So this is x square by 2 tan y plus 3x simply. Okay, next problem. D minus 3d dashed square d plus 3d dashed z is equal to e to the power 3x plus y. So z is equal to phi 1 y plus 3x, and multiplicity is there, so phi 2 y plus 3x plus phi 3 y minus 3x. Phi 1, phi 2 and phi 3, they are arbitrary functions, and pi, that is d minus 3d dashed square d plus 3d dashed e to the power 3x plus 1. Now actually the singularity problem is with this problem, this part, so we keep that. We first process with this one, d dashed e to the power 3x plus 1, and this is d minus 3d dashed, and there 3 multiplied with 1 and plus 3, so this is equal to 6. This is e to the power v, integration e to the power v dv, that is e to the power v itself, so e to the power 3x plus 1. And the next part, 1 by 6, it comes in front of the whole thing, and sorry, there will be a square, and this is x 1 into 2 factorial e to the power 3x plus y, so this is 612 x over 12 e to the power 3x plus y. So then what we can see that as compared to the ordinary differential equation methods, only two methodologies are helping. Number one, you can put all those AB's directly, else if you see that there will be a singularity, then that is f of AB is equal to 0, then the second formula can be applied. Next problem. Square plus 2d dashed minus 2d dashed square on z is equal to e to the power x plus y. So break it like d minus d dashed and d plus 2d dashed. So your CF is equal to phi 1 y plus x, phi 2 y minus 2x, pi. This is 1 over d minus d dashed. See, there will be singularity, so we keep it as it is, and there will be 1 plus 2 multiplied with 1, so it's equal to 1 over 3, and integration e to the power v dv, so e to the power v, that is e to the power x plus y itself. 1 over 3 goes in front of the whole, and next part, x over 1 factorial e to the power x plus y. Actually, I made a mistake in the previous problem. Just check it. There will be a x square, no? Because there is a square. I missed it. So next problem.